Hi, consider the limit of this exponential function, e to the x minus 1 divided by x, as x approaches 0. As is good habit, we'll try to evaluate this limit directly by letting x go to 0. And we get a indeterminate form 0 divided by 0. In the previous tutorials, you used methods like factoring, canceling, perhaps multiplying by a conjugate in order to resolve the limit. But also in the previous tutorials, you were working with functions like polynomials or a ratio of two polynomials, or perhaps something involving the square root. Now we're dealing with functions like e to the x, which is a transcendental function. To truly do this limit justice, we would need to look at the very definition of the exponential function. A definition which invariably involves concepts of calculus beyond the scope of this overview. Instead, we'll use the so-called Squeeze Theorem. With the Squeeze Theorem, we'll be comparing our function to two simpler functions whose limits are readily computable. The Squeeze Theorem involves inequalities, which can be a slippery matter for some. So I'll start off by giving you those inequalities without proof. Our function lies between two polynomials, a first-degree polynomial and a second-degree polynomial. And these inequalities hold near 0. That is to say, our function is bounded by the line and the parabola near 0, but not necessarily far away from 0. But of course, we're taking the limit as x approaches 0, so we only really care what happens near 0. Let's look at a graph. The orange curve is the graph of our function, and the green line and the green parabola are the graphs of the two polynomials. As you can see visually, the graph of our function is always sandwiched in between the two green curves. Furthermore, you can see that near 0, the three graphs approach the same y value of 1, and that's the heart of the Squeeze Theorem. To reflect what's going on in the picture, we'll go ahead and take the limit of all three parts of this inequality as x goes to 0. The limits of the two bounding functions are easy to compute. So it seems that both the bounding functions go to 1 as x approaches 0, so our function, which is always in between, must also go to 1 as x approaches 0. That is, since the limit of our function is a number between 1 and 1, it must be, well, 1 exactly. So this example not only exposed us to a limit we'll surely see again, the problem also demonstrates the essential steps in any Squeeze Theorem problem. Find two functions so that your function is sandwiched in between, at least near the point at which you're computing the limit. Here I gave you those functions for free, that is, without proof. Next, take the limit as x approaches your point. And as long as the limit of the two bounding function is the same, then the limit of your function that's always in between must be equal to that limit. Let's do another example of finding the limit of a function using the Squeeze Theorem. In this example, we'll be looking at the function given by x squared times cosine 1 over x. This function is not defined at x equals 0 because of the 1 over x inside the cosine. But we're calculus students, so this shouldn't stop us from wondering about the behavior of this function near 0, because we can take the limit as x approaches 0. We cannot evaluate this limit directly because of the cosine 1 over x. In fact, the limit of cosine 1 over x does not even exist. Also, you might ask yourself, well, does the limit of x squared cosine 1 over x have a chance of existing? Well, we'll use the Squeeze theorem to show that yes, this limit does in fact exist. And to use the Squeeze theorem, we need to find two functions, say g and h, so that our function is between them near 0. But this time we have to find these functions ourselves, this g and h. So where do we even start? Well, in your first semester calculus course, you'll often see sine and cosine, possibly arctangent, used with Squeeze theorem. And you might want to take a pause to think of why they would want to use those functions. What useful facts do we know about cosine, sine, and arctangent? Maybe a graph will help. So here's a graph of cosine and sine. And what you want to notice here is that both sine and cosine are bounded by 1. That is to say, whatever the input for the cosine or sine is, the output is always a number between -1 and +1. So that's going to be our starting fact. So writing down the fact that cosine is between -1 and +1 will get us started with our inequalities. Next, we multiply everything by x squared. And because x squared is not negative, the direction of the inequalities isn't changed. So now we can take the limit of everything as x goes to 0. Now the limit of both plus and minus x squared is 0. So because the limit of our function is somewhere between 0 and 0, the limit must be 0 itself. Let's look at a graph of this function to see this visually. The orange curve is our function, x squared times cosine 1 over x. The two green parabolas are the two bounding functions. It seems like our function is oscillating, just like you expect cosine to do. And the minus x squared and plus x squared act as an envelope, if you will, for the amplitude of this cosine. Since the vertices of our two parabolas meet at the origin, the function that's in between, our function, must go to the origin as well as x approaches 0. There's nothing special you have to memorize about this limit. It's just used as an example of using Squeeze theorem. In the next video tutorial, however, we'll be using the Squeeze theorem to derive an important limit. It's the limit of sine of x divided by x as x approaches 0. This limit is often referred to as a special trig limit, as it's often used on homework and problems in first semester calculus. We'll use a geometric argument to show that our function is bounded by two functions, and from the graph you might want to speculate on what those functions might be. And as the limit of the two bounding functions is 1 as x goes to 0, we will be able to conclude that the limit of sine x over x as x approaches 0 equals 1. I'll see you in the next video.